And today, Ali will tell us uh, about
I,
modeling atomistic simulations. I hope, I think so. I think Ali will announce his lecture right now. So please, Ali, the floor
okay,
is yours.
perfect. So can you all hear me well?
Yes, yes, we can
Okay,
hear you.
perfect. Okay, so thanks a lot, Sergi, for the kind introduction and for having me. I would love to be actually with you in person. I'm actually at the moment in another workshop in Durban in South Africa. Um, but so I actually didn't announce my title before. This is my fault. But so I perhaps wanted to start off with motivating my talk with this cartoon here. And this cartoon is about something called conformational bias. And so this is me sitting on the computer and I'm asking myself, well, I've heard the rhetoric from both sides. Time to do my own research to tell the real truth. And you do a quick Google search and you find the first link that agrees with what you already believe in. And then you conclude, okay, this is the truth. Okay. And I bring this up a bit to be tongue in cheek, both on the scientific side, and you will see why I'm saying so, but also that in the complex geopolitical climate that we live in, this is a serious challenge in how the public perceives information. So the title of my talk is Chemical Continuum, so overcoming discrete notions in the chemical physics of water. Sergio already told you I am part of the faculty at the ICTP in the condensed matter group at the ICTP in Trieste in Italy. So just to kind of lay the groundwork, my area of expertise and what I'm going to tell you about today is some of our theoretical work in trying to understand the properties of liquid water. So liquid water is a very interesting, complicated liquid, even though it has been studied for, centuries, there's still many interesting and open puzzles about it. And a lot of the interesting properties of water come from its complex hydrogen bond network. So these are these interactions that keep the glue of water together. And so my group and I have been interested in trying to understand the fluctuations in water. And you may ask, well, what is the challenge in understanding fluctuations in water? Well, the root cause of it is that, and you can see it in the simulation that I'm playing here, is that essentially fluctuations in water occur on different length scales and different time scales. And the challenge is how to dissect these fluctuations that can occur on very similar timescales, but on different length scales. So one way to frame that challenge is that in liquids like water, there are a lot of coupled little things happening everywhere. And if you're a physicist, you may be familiar with kind of the language of collective entropic forces. If you're a chemist, you might be thinking about hydrophobicity, hydrophobic, but they're all kind of related together. And this is uh, trying to understand these little things happening everywhere has been a huge challenge in the field. Related to that is that many of the interesting properties of water involve a subtle balance of short range and long range interactions. So, short range, you have interesting quantum mechanical phenomena, electronic polarization, charge transfer that need to be included to get the hydrogen bonding correct on the short length scale. The long range is easy, it's long range physics, which is just electrostatics. Okay. But in some sense, these two challenges here have been a big part of the discussion in trying to understand many of the thermodynamic and dynamical properties of water. And so the title of my talk was called Discrete Notions, or this idea of discrete notions. And so to understand these, let me go back, these fluctuations that happen on these different length scales and time scales, the community has developed a lot of discrete notions. And so one example of a discrete notion is that you should think about water in terms of fluctuations between two local structures, a low density liquid and a high density liquid. And this is thought to dictate a lot of the interesting phase diagram properties of water. Another one is the structure of the excess proton. So this is a proton H plus, you put H plus in water, is it an eigen or a Zundel? And I will tell you more about this as we move along in my lecture. Another kind of discrete notion is what happens when you put ions in water? Are they structure makers and breakers? And I have to say, I hope this doesn't offend anyone, but part of a lot of the confusion in the community is that many chemists have gotten into this field, and a lot of the chemists don't understand fluctuations. And because of they don't understand fluctuations, this has led to kind of the creation of labels that have then created their own fields and directions. And this has had huge implications on how experimentalists interpret their experimental data. And you'll see why as I move along in my talk. So since this is supposed to be a lecture with a school, I thought I'd give something a bit more pedagogical, just to give a historical context. So I want to go back to 1892. 1892, there was Wilhelm Röntgen. So Wilhelm Röntgen got the Nobel Prize for his discovery of X-ray. And Wilhelm Röntgen, this is one of his papers in German, was one of the first people to discover or make the hypothesis that water should be considered as a competition between two types of water molecules. Okay, so that's where the first date goes back to this idea. And just to give you a sense, it wasn't until 1924 when ideas of electronic structure, quantum mechanics were developed by de Broglie and Schrödinger. Okay, so that's a good thing to keep in mind of how ideas come into place of hypothesis before people have a full understanding of things. But then sometimes these ideas get dragged along in history and in time without being revisited. So let's jump forward to 1933. This is this famous paper by Bernal and Fowler. If you haven't read this, I highly recommend it. It's really an outstanding paper. And Bernal and Fowler were X-ray crystallography people. Okay, so they were thinking about, let's say, low temperature, 0 Kelvin X-ray structures. And this was kind of at the beginning of when X-ray scattering measurements were being made for liquid water. And that's what you can see as the plot number 3. And because Bernal and Fowler were X-ray people, they tried to understand the structure factor from coming from the X-ray scattering of water in terms of solid state crystallographic structure. So, close packed quartz tridymite. And that's how they tried to rationalize the different peaks in the spectra. Okay, we now march forward to the 1950s. This was Linus Pauling, who got the Nobel Prize in chemistry. And Linus Pauling, of course, had many contributions. He had a lot of contributions in the understanding of the hydrogen bond, for example. And he was thinking about these things called gas hydrate models. So these are these, cages of gases like chlorine, carbon dioxide, methane, and how water kind of forms these clathrate-like structures, which is typically found or thought to happen, for example, in methane clathrate hydrates that form deep in the ocean. And one of the things I want to point out here, which I hopefully will get to at the end of my talk, is that Linus Pauling was one of the first papers that I found who was thinking about fluctuations in the hydrogen bond network in terms of the empty spaces, so these cavities. And one of the things is what is the connections to hydrophobic forces, which I will try to address later. Okay, so with that history, in comes in about 1970. These were refined models or refined experiments of X-ray diffraction of liquid water. You can see these measurements here done as a function of temperature, done for light water and heavy water, so H2O and D2O. And I just highlight this part in this paper from 1970, which is people are trying to understand what causes these oscillations in the X-ray structure factor. And what they find is that the experimentalists are unable to fit the first peak to a single Gaussian. Okay. And their conclusion is because I cannot fit it to a single Gaussian, then there must be at least two types of water molecules. Okay. And so somehow in this interpretation, just explaining it in terms of fluctuations of environments was not in the picture. And then they make a very interesting statement, which I think is perhaps relevant for the more chemists in the audience, which is they say, however, the implications with regards to hydrogen bonding depends largely on the definition of what a broken hydrogen bond is. And I think this is an important point because it is an issue that has, in some sense, caused a lot of confusion and led to misinterpretations of what is and what isn't hydrogen bonding. And because most of the criteria that are used for hydrogen bonding involve geometrical parameters, which as you will see, can be problematic. So besides the room temperature phenomena of liquid water, from the 1970s all the way to the 1990s, there is been a lot of work on what happens under supercooled conditions. And so this is still a kind of a hotly debated area, but there's more and more evidence now that under supercooled conditions, water exhibits a second critical point. So there's a liquid-liquid critical point, which was initially made as a theoretical prediction, and now there've been more experiments probing this regime, which is very challenging to do because when you cool water, it nucleates into ice. And so fast forwarding to the more recent years, I put this paper up here also for the students. It's a paper that was published in 2018 in Physics Today called "The War Over Supercooled Water," and it's a very, very interesting story, and I encourage everyone to read it because it was a debate that happened between Pablo Benedetti's group in Princeton and David Chandler's group at UC Berkeley on the implications or the understanding of their simulations that were presenting this liquid critical point. And at the end of the day, just to make a long story short, it was discovered after 12, 13 years that the results from the Berkeley group in California were due to a bug in their code. And it had to do with how their thermostats were initiated. Okay, so it's an interesting story, and I encourage you to look at it. But now the dust has settled, and this is, for example, recent simulation published in Science, 40 microseconds of a simulation showing that under supercool conditions, water can fluctuate between a low density state and a high density state. And again, now I've given you this history. The interpretation or microscopic origin of this has been in terms of these local structures, a low density liquid and a high density liquid in terms of local structures. And in order to quantify and characterize this, there's been a zoo of descriptors developed in the physics and chemistry community. I'm just giving you an example of some of them. They measure hydrogen bonding, they measure local density, they measure local tetrahedrality in different ways. The take-home message I want you to take away from this slide is that whenever we build these types of descriptors, they by construction involve a dimensionality reduction. So you're taking a high dimensional system, you're projecting into 2 dimension, maybe 1 dimension, maybe 3, because that's easy to visualize and interpret. But what we've been working on is trying to use information theoretical tools to understand how much information does one lose when you do a projection. And so I show this picture here because it conveys a very nice message. And basically projections, which is what a lot of chemistry and also physics is about, makes nice stories. So this is a picture. Basically, it's of 2 people. If you look at the shadows, one person is smoking a cigar, another person is drinking a glass of wine. but this is a projection of it's a shadow of basically a pile of garbage. And the question is, when one observes phenomena in a simulation or an experiment, typically what you're doing is you're looking at the shadows, but actually you want to know, well, what is the real information? What is actually being projected into the lower dimensional space? So, without getting into much details, because I don't have the time, we've been developing approaches to do something called unsupervised learning. So, we try to take an agnostic view of our data and try to ask, what does the data say for itself without projecting our own interpretations into what we wanted to see? And so this starts by using something called local atomic descriptors. These are essentially agnostic ways of encoding the information of the local density of an environment in kind of a variational way, where you include radial basis sets and spherical harmonics. Okay. From that, you can do a dimensionality reduction. We do something called this intrinsic dimension estimator, which allows you to determine the correlations in your data and therefore learn what is the real dimensionality that the system lives in. And then we use something called a density peak clustering, which allows us to construct the free energies or the probabilities in the high dimensional landscape. And if I'll share the slides with Sergey at the end, so you can take a look at these references. So I just want to show you a few results. We've looked at room temperature molecular water, different types of water models, TIP4P, and SPC are these point charge classical non-polarizable water models. MBPol is perhaps the most accurate water model on the market. It takes into account many body polarization, and we do the analysis that I showed you before. So, assuming nothing about hydrogen bonding, and if we construct the free energy landscapes, the take-home message here is that we never find any evidence for two states, two local structures. This is at room temperature. So basically, the effective physical picture of the free energy landscape is like a crater, okay? It's a flat crater with lots of different minima populated by lots of defects, non-defects, and then the free energy rises steeply on the sides, and it's essentially a flat free energy surface with ripples, as you would expect for a liquid, but there are no two locally favorable structures as many in the community who have tried to interpret. Okay. So now let's move on. The other discrete notion I told you was about the structure of the proton. So this is it's a very fundamental, let's say, problem. You take a hydrogen atom, you pull out an electron, and you create a proton, H plus. But now if you put H plus from the gas phase into water, it does all sorts of interesting chemistry. And again, there's been a huge, long history of the chemistry community looking at what is the structure of the proton. And so this is a classic paper by Manfred Eigen, who also got the Nobel Prize. And I'm just listing here all the different experimental methods that have been used to characterize what the structure of the proton is. And if you look carefully, many of these initial experiments were done in cold gas phase clusters and crystals. Okay, so that was a bit the context, and this has been a long-standing debate between these two people, Manfred Eigen and George Zundel, left and right. And basically, Manfred Eigen believed that the excess proton, so it doesn't exist as H plus, it's now chemically interacting with a water molecule, so it's H3O plus for the chemists. And on the other side, Zundel believed that actually it was H5O2 plus, so the proton is delocalized. And the experimental community and also the theory community has been fighting for the longest time about which is the dominant structure in water. And so I remember when I was a PhD student, I was attending, let's say, many of these meetings in the US, and there were, one year someone says, well, it's eigen, the next time it's Zundel, then someone else comes with some new simulation and experiment. No, actually, it's an eigen-like structure. Another one says it's Zundel-like. And now, in the very recent years, there's been another paper that has shown, well, actually, or suggested it's a distorted eigen-like structure. And again, part of the challenge, um, and the reason why there are all these types of arguments, which are essentially mostly semantics, is that um, people look at these structures, they try to interpret them in a reduced dimensional space and using chemical coordinates that often bias the interpretation. And so there's really been a whole, I mean, thousands and thousands of works on this from the 1990s to 2024. Um, this is, in fact, this whole field started off with some pioneering work by Michele Perinello, who developed a technique called Carr-Perinello ab initio molecular dynamics. Those were theoretical predictions. Then, for the last 15 to 20 years, there's been a slew of experimental methods. Or experimental techniques using IR, Raman spectroscopy, and I'm just showing you here some of these new examples. And then this has in turn led to an influx of theoretical and molecular modeling, especially now with the explosion of machine learning techniques. So this is a very interesting field to see how theory drove experiment, and experiment is driving theory again. So I decided to try to say, okay, well, let's take an agnostic approach. What does unsupervised learning have to say about the proton structure? So if you start with cold clusters, so cold clusters means a proton immersed in a cluster of 20 water molecules at 50 Kelvin. And there are experiments on this. I don't have time to get into the details, but where it is thought that there is something like an eigen versus a Zundel. And if we do our unsupervised learning approach, and I'm just showing you here the projection in 2D, it's actually living in a very high dimensional space, but it's easier to visualize in this way. You get two clusters. So at low temperature, cold conditions, clusters, you get eigen and Zundel. What happens when you go to the condensed phase? So you go to room temperature. This is now hydrochloric acid. And what you end up seeing is that you have one big minima here. This is the neutral water cluster that I showed you earlier on. There's another neutral water cluster over here, which corresponds to a defect. And that defect is illustrated in this picture here. So it's a water that donates two hydrogen bonds and accepts one. And there's only one, and only one protonated charged cluster. So in the condensed phase, at room temperature, eigen and Zundel basically no longer exist. And from the point of view of thermodynamic states, they're not stable, and they just exist as one big continuum in a single thermodynamic basin. So you may ask me, well, why is all this important? Yeah, it seems like I'm fixating on a lot of nomenclature and language. And so I want to go back to actually some old experimental work that I was involved in. And these are Raman experiments of water and the excess proton in water, so HCl. The top panel is experimental IR and Raman for the proton water. The bottom one is what we get from our calculated Raman and IR spectra. And I want you to focus on the IR. So the IR, when you put an hydrochloric acid, has a broad continuum of absorption between 1500 and 3000 wave number. You see from our theory that we also, essentially predict the same trend. This was in 2018, and we were trying to understand how do we interpret this broad continuum in terms of the eigen and Zundel species. So we did our at the time, the reduced dimensionality, the dimensionality reduced coordinate, which is on the x-axis here, and we tried to separate out clusters that were eigen and Zundel, and those are shown in the two different colors. But what you see here is essentially both eigen and the Zundel absorb and overlap in their absorption in this broad continuum between 1,000 and 2,500 wave numbers. And my take-home message here is essentially that this partitioning that we had done in 2018 was essentially wrong. And it's a partitioning that we did because we were wanting to look for a two-state picture in the data, but it doesn't exist. Okay, and so the right way to describe this is that you have one basin characterized by fluctuations, and these fluctuations are essentially what lead to this broad continuum. And if you come from a more physics background, the way to think about this is that the proton is an ionic topological defect in the hydrogen bond network. Okay, so in the last part of what I want to tell you, I want to move into a topic called hydrophobicity. So this is the thing: water doesn't like oil, right? That's why they demix. And so again, to give you a bit of a historical preview, this is a very interesting paper by Charles Tanford, who reviews a bit the historical context of where ideas of hydrophobicity came. And actually, this is a very sort of interesting historical note. I don't know if many of you know about it, but there was Dorothy Rinch was a mathematician who got interested in biochemistry. And she was trying to understand, why do proteins fold? Why do they have a stable helical or sheet structure? And she came up with something known as the cyclol hypothesis. And so her idea is, if you have these two amide groups in a peptide, they come together, there's a chemical reaction leading to a proton transfer that leads to a covalent bond between the nitrogen and the carbon, and this leads to the secondary structure being very stable. Now, if you're a chemist and you see this, you say, well, this is impossible, right? I mean, and we know that this is not what stabilizes proteins, at least most proteins. And so Dorothy Rinch was very obsessed by this hypothesis, and she was trying to convince Irving Langmuir. So Irving Langmuir was another famous physical chemist who developed this idea of a Langmuir isotherm, and he was interested in how does surface tension of an interface change when you add stuff, soap, surfactants into the solution. And so he actually believed or thought that Dorothy's idea was rather credible, and he was, I think, one of the first people to invoke some idea of hydrophobicity. And so I took this snapshot here of where Irving Langmuir says, that a stabilization of about 2 kcals per mole will result when two hydrocarbon groups combine with each other instead of with water. And this idea was put forward to seek support for the hypothesis that I told you earlier on by Dorothy, which was in fact wrong. But this was the first kind of reference to hydrophobicity, which is that hydrocarbons, and this is what we think, hydrocarbons do not interact with water because they're non-polar. So, and this idea that hydrocarbons cannot interact with water comes from a very classical view of hydrocarbons. It's where we don't think about the electronic structure. We don't think about what happens when you have a hydrocarbon embedded in or hydrophobic or dipolar groups. And it's an example of another discrete notion. So things are either hydrophobic or hydrophilic and not kind of in between. So I don't have time to get into this, but together with my collaborator Sylvie Roki in Switzerland, we've been trying to understand this deep relationship between hydrophobicity and the quantum mechanics of electronic structure. And what we have shown, or what we think at least, is that if you take a hydrocarbon and you put it in water, there are situations where you can have some highly non-trivial electronic polarization and charge transfer that exists between the water and the hydrocarbon due to the orientational polarization of the solvent. And this energetic stabilization can add up to about kBT, thermal energy. Okay, so it's not small. So hydrocarbons, of course, interact much weakly compared to polar groups, but there's some interesting things that can happen when you start to think about the electronic degrees of freedom. So that's on the kind of the electronic side. Um, Taking now a step back into the historical evolution of the ideas, Linus Pauling introduced the idea of cavity formation, and then Kauzmann started thinking about how does water structure change when you put a hydrophobe in there. And so there were these ideas that if you put a hydrophobic molecule, water doesn't like it, it structures around it, to reduce the entropy, which reduces the entropy. And the idea is that hydrophobic effects is a way to bring these hydrophobic molecules together to compensate for that entropic cost. And David Chandler, or the late David Chandler, developed these ideas on what is the thermodynamics of creating cavities in water. And this kind of is in the spirit of classical nucleation theory, which is that there's a competition between volume and surface area. So at small length scale, volume dominates. At large length scale, surface area dominates. Okay? And this entire picture was based on idealized spherical objects in water. Now, the physicists like to, everything is a sphere, right? But if you're a chemist, you know this is not true. Chemistry matters, geometry matters, roughness, molecular scale roughness matters. And so this is something that, well, we did a couple of years ago. We asked ourselves, well, is it really difficult to solvate hydrophobic polymers? So we took simple Lennard-Jones particles. So the top panel is the Lennard-Jones polymer in a molecular dynamics simulation surrounded by a cavity. In the bottom panel, these are the cavities, voids, empty spaces that we see in liquid water without the polymer. Okay? And so this is kind of a Gedanken experiment that you can do on the computer only, which is we asked, what is the free energy required to solvate a hydrocarbon like dodecane? And so we took two polymers, something that looks like a wire, another one that has a branch, or it looks like a small cat. And you see here, for example, the one on the right, we can find a cavity, a shape in liquid water that is looking similar to the shape of the polymer. Okay? And if you do the thermodynamics, what you find is that the solvation free energy of the hydrocarbon is about 20 kilojoules per mole, and the free energy to create the void of that shape is about 17. So essentially, the take-home message is here that thermal fluctuations in water create cavities that it doesn't cost a lot to solvate a hydrophobic molecule, essentially. So we've extended this now, and this is the last thing I want to share with you, to amino acids. So we've taken the 20 amino acids. We've looked at the shapes of the branches or cavities in which they sit. So for example, I'll show you here. This is the case of proline down here on the right. Proline is an amino acid, right? And if you look, you might think, well, the cavity in which it sits is going to be compact, but actually it has lots of branches and can spread far away from the amino acid. And depending on whether you add charge or not, you can reduce the size of these branches. Okay? So we asked ourselves the following question: can we predict thermodynamics from the shapes of cavities? And so the traditional picture is, let's use the volume and surface area. And our picture was, well, maybe you need more than volume and surface area. Maybe you need the topography of these shapes or the branches to describe the thermodynamics. And to make a long story short, essentially, we develop very simple linear regression models that regress things like the free energy, the enthalpy, the entropy from experiments against a linear combination of variables, including volume and surface area, and three or four other branch variables that describe the geometry and shape of the variable. And then one final thing, you can also build models that link the chemistry to the shape of the void. And so basically, what this is telling you is that this is a bit of the picture is not so clear, but in the second panel here, the volume, the surface area of the cavity can be predicted in terms of a linear combination of the chemical properties of the amino acid, its mass, its number of polar groups, its van der Waals volume, and so on. So basically, chemistry of the amino acid and the shape of the void and thermodynamics seem to be, let's say, all very entangled together. So that's essentially what I want to tell you. Before I end, I wanted to thank all the various collaborators who've been involved in this project. So the list includes basically everyone. In the blue, the people colored in dark black, sorry, are the people that specifically contributed to some of the things that I told you about. And finally, I want to thank funding agencies. I want to thank the ERC for their money, essentially, and a previous Horizon 2020 project which funded some of the postdocs. And I'm happy to take questions.
Okay, thank you very much, Ali. Let's thank our speaker. So, dear colleagues, we have a few minutes for the questions. Please, in our audience in Zoom, please raise your hands. Probably people are thinking about questions, and Ali, I would like to. I have a lot of questions, and I know that we are limited in our time, and I would like to.
Go. Yeah, I mean, you can ask whatever you want.
Yeah. This is very interesting results that you show about critical point that people are looking for, and this critical point is already detected. Actually, we can definitely say that we have the second critical point in liquid water, this low density, high density, or this is still is.
It's so
problem.
Okay, different people will tell you different things, but I'll tell you my perspective, which is that there's a strong, let's say, I think simulation, or there's strong suggestive simulation evidence that there is something appearing from the simulations as a second critical point under supercool conditions. That's the theory. On the experimental side, there was until the last 10 to 15 years, that whole region of the phase diagram was kind of called no man's land. Now, there are more and more experiments that seem to be indicating that there's some credence to this. I think there are still challenges on the interpretation of what these experimental signals actually come from. On the theory side, there are huge challenges of sampling finite size effects. And so
I see.
Yeah.
Okay. So thank you very much. And also we have another question, Professor Francesca Mocci, please. Francesca?
Thank you very much for this excellent talk. Very interesting.
Thank you.
If I understood correctly, in the last part of your presentation, you estimated the cavity formation energy using force field.
No.
Okay.
No. So sorry, I didn't. Yeah, these are basically existing experimental measurements of the free energy of solvation, the entropy, and the enthalpy. And we're using that from experiments. We are doing simulations to extract our cavity variables, and we're building models based on those variables and saying we can predict those experimental free thermodynamics. I have to
Okay.
say, I think all those experiments need to be repeated because they were done in the 50s and 60s, and there are lots and lots of problems in these types of experiments, and so it's not a very interesting experiment to do, but I think it must be repeated because it's used as benchmarks for many of the computational models out there. So yeah, but yeah, thanks for asking that because that's a good clarification.
Thank you.
Thank you.
Thank you very much, dear colleagues. Other questions in Zoom, please? In our audience, there is no questions. Yes, there is one question in chat.
Let me see.
Yes. So, from what I understand, water itself creates voids that may accommodate hydrophobic molecules. But does the presence of hydrophobic molecules influence the shape, number of those voids? This is from
Yeah,
James.
that's a fantastic question. So, right. So the presence of the hydrophobic molecules definitely influences the size and shapes of the voids, and no surprise, if you have a hydrophobic molecule, it tends to create much more branchy and larger cavities and voids. When you go to polar groups, what's kind of interesting is that systems with a plus charge are nominally look more hydrophobic in terms of cavity shape than systems with a negative charge. And part of the origin of that is that negative charges tend to polarize protons. They orient the water dipoles, and so whereas cations don't orient waters as well because it's usually the oxygen that points to the positive charge. But yes, they certainly influence it, and they influence it in highly complicated ways, and it depends on the size of the molecule. It depends on whether the hydrophobic molecule has something. Is it connected to something that's positively charged, negatively charged? What's the shape? So yeah, I think there's an entire phase diagram of in the axis of geometry and chemistry, which is missing from the current theories on hydrophobicity.
Okay, thank you, Ali. We have another question, Professor Sonia Grubisic, please. Sonia?
Okay, so thank you for this interesting lecture, Ali. So when you was speaking about hydrogen bonding, forming and breaking, I'm interested how it can influence the conformational transformations of the molecules embedded in water.
Okay, thanks very much for that question. So this depends a lot on what region of the phase diagram you're at and what the size of your molecule is. So hydrogen bond breaking and forming of water is typically I don't know, couple of picoseconds. Maybe near a big protein, it might slow down to, let's say, I don't know, 50 to 100 picoseconds. If your conformational change is happening on a much slower time scale than that, then in some sense the protein or the molecule is a much bigger and heavier object. So the water molecules in some sense just adiabatically respond to the fluctuations of the protein. That's what I would see at room temperature. However, if I would go to low temperature cryo conditions, then I think the story would change. And I don't have data to support what I'm going to say, so I'm just speculating. I think there you need much larger scale reorganization of and fluctuations of the water hydrogen bond network to facilitate conformational transitions. But yeah, so it really depends, and there are cases where you need to include the solvent to determine the activation barriers for conformational changes. There are other cases where the conformational change is happening so slowly that the solvent is a fast degree of freedom, so it's not doing much. It just what the water does is it's more acting like an effective friction coefficient that lubricates a bit the fluctuations of the protein or the molecule.
Okay, thank you. And I have just one comment maybe about this transfer. It's also interesting. CHO when you spoke that this charge transfer can stabilize the lipids or some hydrocarbon molecules. I think this effect is already embedded in some force fields implicitly.
Yeah. It is effectively there. Yes, I would agree. And I think the problem is that there's not enough experimental spectroscopy, vibrational spectroscopy data on proteins to validate and understand whether the force fields are getting this right or wrong, because the phenomena that really gets affected is the vibrational frequencies, and that's a hard thing to get with the force field. So vibrational spectra are very hard to get with force fields, and so but yeah, I agree with you. Effectively, some of these things are encoded in there.
Okay, so thank you very much.
Thank you very much, Anya.